So according to my schedule, we need to review a little thermochemistry. Look at the review document problems. I'll pick out a few. Let's see. Be closer. Okay. Looks like I've got the whole first page checked. Okay. Any questions, problems that we need to deal with before we get into this particular items that are giving you trouble? Okay. This might be a short review. Okay. Number one is a gas absorbs no heat, 0 joules, but it performs 30.7 joules of work. The change in internal energy of the gas is what? Work it backwards. What's internal energy? It's heat plus work, correct? Okay. Remember, everything, the sign convention is relative to the system. So if it's going in, it's positive. If it's coming out, it's negative. Okay. So we've got to ask ourselves, since there's no heat change, right? There's no change here. That term drops out. That's 0. But there's work being done. So if the gas performs work, we have to decide what is the system. Well, the system is the gas. So this is our system. And if it performs work, which way is it? Was the work going? It's going out, right? So it has to be negative. And it's a negative 30.7 joules. So that's why the answer is D. Okay? That was just a review of that formula and sign convention. About 2. What's the kinetic energy of 1.56 kilogram object moving at 94 kilometers per hour? Okay. Remember how to calculate kinetic energy. Okay. If our answers are going to be in joules or kilojoules, then we have to use fundamental units for velocity and mass. So mass has to be in kilograms. Okay, that's good. It's already in kilograms. Kilometers per hour. That's not standard velocity. Like velocity should be in meters per second. So this one has to be changed. We say 94 kilometers per hour. Right. When you got, I said this at the very beginning, but I'll say it again. When you've got a unit conversion that requires converting 2 units in the same number, 2 units of measure, do one at a time. So I'm going to take kilometers first. 1 kilometer is 10 to the 3rd meters, 1,000 meters. Okay, that takes care of that one. Now, how about hours? Okay. We'll come down here. Got to get rid of hours and leave us with seconds. So do you know how many seconds are in an hour? If you don't, then we can do it. We can just chain them together. So instead of that, let's get rid of hours this way. 1 hour is 60 minutes, right? So the hour's going. Oops. Oh, sorry. Numerator. Denominator, numerator. Minutes. 60 minutes per hour. Got the hours going. Now we got to get rid of the minutes to make seconds. So 60 seconds in a minute. There you go. So we need to take this one times 1,000 divided by 3,600. Okay. We're going to take 94 and 1,000 and then divide by 3,600. So that's, let's see, three significant figures, 26.1. So velocity is 26.1 meters per second. That term is squared. And this term is 1.56 kilograms. Okay, we do that calculation, our units will be in joules. So I've already got that one in my calculator. Let me just square it. And 1.56 times and divide by 2. So I get 532 pretty significant figures. 532 joules. Okay. Did I do that right? Keep checking again. 94, 1,000 divided by 36. 26.1. 26.1. Square that. Okay, and then times 1.56 kilograms, and divided by 2. Yeah, 531 joules. Joules. So how many kilojoules is that? 5.31 times 10 to the minus 2. Oops, nope. How many kilojoules in a joule? How many joules in a kilojoule? Thousand. Divide that by 1,000. .31 times 10 to the minus 1. There we go. Now, there it is. Well, that's the closest one to it. Several steps to get that one. All right. Let's see if we need to. I can see the handwriting on the wall. Eventually, I'm going to have to invest in a better clicker. Which of the following statements correctly describes the sign of Q and W for the following exothermic process at 1 atmosphere pressure, 370 K, where water goes from gas to liquid? Okay, is that an exothermic process? Yeah, if the system is the water, it goes from a gas to a liquid. In order to go from a gas to a liquid, it has to lose heat. So heat has to leave it. So that is an exothermic process. So in this system, right, water gas is going to liquid. So that means heat has to leave it, which means it's negative Q, right? Okay. And the pressure is constant at 1 atmosphere and temperature is constant at 370. So if the pressure is constant, how do you keep the pressure constant on a gas that's condensing? you've got to allow the volume to decrease, don't you? All right, let's do it this way in a cylinder. So you have water vapor with a certain pressure on it, 1 atmosphere. Right. The temperature is constant at 370 degrees, or at 370 K. Okay, when we do it this way, as that gas condenses, it takes up less volume, right? For the same pressure, it's going to decrease. So that means work is being done on the gas because we're going from this height to that height. So if work is being done on the gas, work is positive. So let's say Q is negative. They're not both negative. Q is negative, here we go. And W is positive. So there it is right there. That W took a little work. Right? If you look at it this way, it looks like that's a rigid ball. It's not going to change. If that happens, then the pressure would actually decrease in here because we'd have fewer moles of gas. Right? And according to our gas laws, the pressure should decrease, but we can't let it decrease. So the only way you do that is decrease the volume. And this is a better picture of what's actually happening. Oh, that was from a previous one. Okay, for a particular process, Q is 20 kilojoules. So I'd say that's positive. And W is positive 15 kilojoules. Which of the following statement is true? Let's see. If our system is plus 20 kilojoules of Q, and work is plus 15 kilojoules. Okay. Heat flows from the system to the surrounding. Nope, that's false. It's going this way. The system does work on the surroundings. Nope, it's positive. Surroundings are doing work on the system. Okay. How about delta E equals 35 kilojoules? Well, let's see. Delta E equals Q plus W, right? 20 plus 15 is 35. That was true. All of the above are true? Nope. None of the above. Okay. C's the answer. All right, let's see. Let me look at 5. Which of these are correct? The internal energy of a system increases when more work is done by the system than heat was flowing out of the system. All right, now we're going to have to look at that. Let's draw a picture. Here's our system. And internal energy is, so we've got Q and W. I don't know which direction they're going yet. The internal energy of the system increases when work is done by the system. So this would be negative. Heat is flowing out of the system. Heat is flowing out of the system. That's negative too. So the internal energy cannot increase. I mean, they're both negative, right? So it doesn't matter which one's bigger. All right, so that was false. How about this one? Internal energy of the system decreases when work is done on the system. So now we're going to turn it around. Work is done on the system. And heat is flowing into the system. So that's positive also. So that can't be true either. Internal energy is actually getting bigger. It means it's going more positive. So it's not decreasing. All right, so that was false. The system does work on the surroundings. Work on the surroundings. Okay. This one again. When an ideal gas expands against a constant pressure, it will. Okay. Yeah, that's true. I mean, that's a simple statement of what happens under constant pressure. Right? Change of pressure is 0. It's constant pressure. So if the system is doing work on its surroundings, work is leaving. And that happens when a gas expands against a constant pressure. That's true. That statement right there, we don't even have to think about it. That's true on its face. Okay, let's see. Got some checked off. Let's go down to 7. There we go. 1 mole of an ideal gas is expanded from volume of 1 liter to a volume of 8.93 liters against constant external pressure. Okay. How much work is performed on the surroundings? All right, let's draw our picture. Expanded from 1 liter to 8.9 liters. So our gas starts here at 1 liter and it expands to 8.93 liters. Okay? And 1 atmosphere pressure. Okay? So what's our formula for an expanding gas? Work equals minus P delta V. Right? Okay, so that will be in units of liter atmospheres. Right? Okay. That we have to do that first. So the volume change is 7.93, right, times 1. So it's a negative 7.93 liter atmospheres of work was done by the gas on its surroundings as it expanded. Okay. Now we have to convert those units measured to joules. That's what this is for right here. 1 liter atmosphere equals 101.3. So liter atmosphere here is 101.3 joules. We multiply those. $7.93, I have to change the sign. 101.3. So I get rounded off to 3 places, minus 803 joules. There it is. Okay, so I had to do 2 things here. We had to remember this part, and we had to make the conversion. How about, let's see, let's get to 12. Here we go. Calculate the work associated with the compression of a gas from this volume to that volume. So work is being done on the system. So we're positive. We're putting work into the gas at a constant pressure of 13.1 atmospheres. Oh, okay. That's not that bad. So if it's going from this one to that one, then it's a change of what? 121 minus 80 is 141 minus 41 liters. That's 0.0. And at a constant pressure of 13.1 atmospheres. Okay, so this is a negative times that value. But when we calculate work, it gets a negative sign here also, right? And that makes sense because if we're compressing the gas, we're doing work on the system and it needs to be a positive value. So that's 41, oops, times 13.1. So that's 537 liter atmospheres. Positive 537. Okay, you know it has to be positive because work is being done on the gas. Okay. Let's see. Let's skip down to 19. That's without scrolling. Almost. Which of the following properties is or are intensive properties? Is mass an intensive property? When we describe mass of something, it changes with how much of that substance you have, doesn't it? So that's an extensive property, or capacity factor, I like to call it sometimes. How about temperature? What is temperature? It's a measure of the average kinetic energy of all the particles in the substance. And you measure the temperature anywhere in a substance that's equilibrated for its heat, then the temperature will not be different. It'll be the same everywhere. So that is an intensive property right there. How about volume? If you have more substance, you have more volume, right? Okay, so that's extensive. How about concentration? That's intensive, right? So much moles per liter, concentration of a solution. It doesn't change with how much you have. Energy. Yeah, that changes. If you have more heat or more work being done, you got more energy. So the only two intensives are 2 and 4 right here. About 22. Scroll down. Okay. What is this stuff right here? Recognize it? That's okay if you don't. That's ethanol, the drinking kind. If we burn it, we get carbon dioxide and water, and this is the amount of heat that we expect to get from it. See that negative sign? That's exothermic. This is the enthalpy change for that reaction. So, which side contains more heat, more energy in their bonds? This side over here. Because exothermic reaction, the best way to think of exothermic is the energy from enthalpy is a term on the product side. It's giving up heat. It's one of the products. Whereas endothermic, we put it on this side, and it would have a positive sign there. Okay, let's get to the question. This is a balanced equation. And which of the following is true? The reaction is exothermic. Yep, that's it right there. Exothermic. The enthalpy change would be different if gaseous water was produced. That is true. If the phase changes, if you have a different phase for the reaction, the enthalpy changes. These phases are extremely important in correlating them with a particular enthalpy. Usually what's done is the phase of the reactants and products is the phase that it would be at standard temperature and pressure. And for chemical reactions, if it's, well, for any chemical reaction, remember when we were talking about just purely gases and their physical behavior, standard temperature was 0 degrees Celsius. But for chemical reactions, the standard temperature is 25 degrees Celsius. So if it's anything besides 25, well, if we let it go up to 100 degrees, then that will change to a gas. So these are under standard conditions. The enthalpy change would be different. Yes, that's true. The reaction is not an oxidation reduction. Do you remember that? That rule of thumb? You've got a combustion right here. You have an oxidation reduction reaction. So that was false. The products of the reaction occupy a larger volume than the reactants. Well, let's see if that's true. Well, let's see. This is a liquid. That doesn't count. That doesn't count for volume. Not significant. What you want to look at is the gases. That's 3 moles of oxygen, 2 moles of carbon dioxide. The volume actually goes down. So that one's false. The only 2 true are the 1 and 2. These right here. Okay? It's 22. About 26. Okay. 32.5 gram piece of aluminum with a molar heat capacity of this 24 joules per degree Celsius mole is heated to 82.4 degrees and dropped into a calorimeter containing water with its specific heat initially at that temperature. The final temperature of the water is 24.2. Calculate the mass of the water in the calorimeter. Okay. This looks like a big problem, but it's really not. It's a standard calorimeter problem. So what do we have going on here? We've got aluminum that's going to change temperature, right? So it's going to be a heat change, a Q. And we also have water. That's a heat change. Does it say to ignore? Yeah. No, it says ignore significant figures. It should also say ignore the heat capacity of the calorimeter, which we can't do in real life, but for a problem like this, we can. So we've only got 2 terms, right? Remember, an isolated system is our calorimeter. The change in heat is 0. Everything that happens in the calorimeter stays in the calorimeter. So everything has to add up to 0. So we've got the Q of the aluminum plus the Q of the water. Okay? That's where we start. Then we resolve what these Qs equal to. So Q of aluminum is going to be S specific heat capacity times its mass times change in temperature for the aluminum. And then the same thing for the water. S for the water. Actually, I should put aluminum here because they have different specific heat capacities. There we go. And then the mass of the water, and then the change in temperature for the water. Okay? We'll take it a step at a time. All right. Let's see. I guess I can do part of it here. So what's the specific heat capacity of aluminum? 24.03 joules per degree C mole. 24.03 joules per degree C mole. Mole. Okay. You know what? I can see a problem already. Because this is in terms of moles, not mass. So we need to change our formula, don't we? For the aluminum, this needs to be moles of aluminum in order to cancel out that mole. Okay. How about water? Did they give us, calculate the mass of the water? Okay. And this one, the specific heat capacity for water is in joules per gram degree C. Okay. So we can leave the water alone. We just need to convert 32.5 grams of aluminum into moles. And it's, what is it? 26.98. 26.98 grams per mole. All right. All right, so we got 1.205 moles of aluminum. Okay, now we can put this in for aluminum. 1.205 moles of aluminum. Okay. Now we need a temperature change. So what's the temperature change of the aluminum? Remember, it's always final minus initial. So the final temperature of aluminum is what? It's the same as the water, right? When you reach equilibrium, thermal equilibrium, the water and the aluminum are the same temperature. So it's 24.2 minus its initial temperature, 82.4 degrees. Okay, that's aluminum. Now we got water, 4.18 gram per, joule per gram degree C. And what's the mass? That's the unknown. Now it's temperature change. Final temperature is 24.2. What's the initial temperature? 22.3. Right here. There we go. Now we just need to solve for the mass. Right? Let's see, do I have time to do that? We'll give it a go. Let's do it in stages. Let's do this one first. 24.2 minus 82.4. Minus 58.2 times 1.205 moles times 24.03 joules per mole degree C. And that one is minus 1685. This one right here. Minus 1,685 joules. This one, what is that? 24.2 minus 22.3. That's 1.9 degrees. Times this value, 4.18, is 7.942. So this term is 7.942 times mass of the water. Plus, and that's equal to 0. So if we add this to both sides, we get that one on that side over there. 1685 positive, and then we divide it by this one, and that gives us the mass of the water. So I just go over here and change that sign, and I go back, flip it back, and divide by that value. And I get 21.2, 21.2, no, 212. 212 grams of water. Okay? I mean, we danced around the barn several times to get there, but this is just an illustration of how methodical you have to be when you do these calculations. And always be thinking, right? If I hadn't been thinking, if I'd been rushing through, like if I were taking a test, taking one of my own tests, I might have made a mistake. And instead of putting moles in there, I might have put the mass in there. And I'd be willing to bet that one of those answers is calculated just that way. That's how sneaky multiple choice tests are. Just because you see the answer you got doesn't mean it's the right one. Okay. 26. Just flip on down. Oh, we're going to skip a bunch of. Must have been a lot of repetition. Keep going. 52. I thought so. Here we go. All right. So in this one, we want to find out what's the heat capacity of the calorimeter. Remember when we actually go in the lab and do the calorimeter lab, which should be week after next. Yeah, so next week I'll give you that hard copy for you to prepare. The calorimetry lab, we have that total, and we have the heat capacity of the calorimeter that we have to consider. Okay, plus whatever other heat changes there are. Maybe there's water in there, or maybe there's Q of the reaction. Maybe we have a reaction going on in the vessel in a solution. So there's an amount of water, plus there's a Q produced by the reaction. And then the calorimeter either absorbs or gives up heat. If it's an endothermic reaction, it might suck some heat out of the calorimeter. We have to account for that. So what is Q if we're dealing with calorimeter? It's just that big C times the change in temperature. Okay, so if this is in joules, this is in degrees C, then this one has to be in joules per degree C, right? To cancel the degree C. All right, so let's see, we have enough information to do that. The heat of combustion of benzene is this much per gram. So if you combust 2.82 grams of benzene, how much heat should you expect from that combustion? Minus 41.74 kilojoules per gram, and we're going to combust 2.82 grams. Okay, grams cancel, leaves us with kilojoules. So that gives us, actually this gives us that term right there. Oh, excuse me, no it doesn't. Hold on a second. Temperature to rise 3.29 degrees C in a certain bond calorimeter. Okay, so what we've got here is this here. There, that's the Q of the reaction. So this is the Q of the reaction. Let's see. I better do that again. Uh, 117.7 kilojoules. Okay. So this is minus 117.7 kilojoules. Or if we want to, okay, notice the answers are in kilojoules. So we can leave it as kilojoules. Okay. And then the Q for the calorimeter is this one right here. We substitute for this in the Q. So this is the calorimeter constant times the change in temperature. And that has to be equal to 0. What's the capacity? Causes the temperature rise of 3.29 degrees C in the calorimeter. So the temperature change is given to us, 3.29 degrees C. Okay. So we just take this one on the other side, make it positive, and divide by 3.29. So I get 35.8. Let's see. 35.8 joules, kilojoules per degree C. There it is right there. Okay, did I lose anybody in that discussion? Okay, because I get the feeling I almost lost myself. So that's why I'm asking you if I lost you too. Okay, that was 52. Let's see. Ah, 65. Good. I didn't have to scroll. All right, this one. This one uses Hess's law. We have this equation with this enthalpy, this equation with this enthalpy, and neither one of them describe the enthalpy of formation for copper 2 oxide. So first you have to know is how do you write the equation for the standard enthalpy? You start with the product. So this is the product. That means we want to end up with that. So in order to do that, you need the elements in their standard state. So this copper solid plus O2 gas. Okay? Now, you can't touch this. It's always 1 mole. Always a coefficient of 1. So we have to use fractionals over here. One of these, that's good. This one is 1/2. Okay, so that's the target equation. And we want to use these equations to equal that one. Okay, so we need copper oxide on the right-hand side. Here it is. We'll use this one as is. Okay, well, that was good. And the other one is also copper oxide. Okay. But are the others on the correct side? Copper's over here? No, copper's not on the right side. My mistake. We use this one the way it is. This one has to be inverted because we need copper on this side. So this one will be copper plus copper oxide yields copper 1 oxide. And now the delta H is equal to minus 11 kilojoules. Okay, so we're going to use this one. Now let's see if we add this one together with that one. Will it give us the equation we want? There's one copper. Right. Copper. How about oxygens? We've got half an oxygen here and no oxygens here. Okay, so that's good. We used this one from here, and we used this one from here. Now, what about the others? There's copper oxide. Oops, excuse me. There's copper oxide, and there's 2 of them here. Right, so this cancels 1. But this one, where are we? This one cancels. Hold on a second. Let me write those out over here. Copper 2 oxide plus 1/2 O2 yields 2 copper oxides. And then we flip this one around. Now we've got copper on this side plus copper oxide yields Cu2O. That leaves us with a copper oxide here. I wonder if that equation is written correctly. Oh, duh. Nobody's going to correct me. That's what we want. We want one on this side, right? So that cancels that, leaves one of these, cancels that one, leaves one of these. There's that one. Okay. This one cancels that one. And this one is there. That one's there. Okay. So when we add those together, we get the equation that we were looking at. And now we just add these together, which is minus 155 kilojoules. Here. I thought I was seeing double. Okay, that was 65. Let's see. How about well, I just give up. Seems like there ought to be more to it than that. I'm gonna pick some out. Those are the only ones I've marked. So let me pick out one that looks interesting. How about this one? Yeah, there we go. 8-4. Consider this reaction. Aluminum and chlorine make aluminum chloride. And that appears to be balanced. 2 aluminums, 6 chlorines, 6 chlorines. Yeah, that's balanced. This is the enthalpy, right? So obviously that reaction is exothermic. But the interesting part I wanted is this one. How much heat is produced or required when 10 grams of aluminum chloride forms? So we're starting off with 10 grams. Well, actually, it's a product, 10 grams. Okay. So, how much heat is produced or required when 10 grams of aluminum chloride is formed? Well, this is in terms of moles. We can't go by grams. So we have to convert this to moles. How many moles of aluminum chloride is formed? Okay. So 1 aluminum and 3 chlorines. Aluminum is 2698. So aluminum is 2698. And 3 chlorines, 3545. And 26.98. So I get 133.33. 133. As the molar mass. So we divide that into 10. And I get 7.50 times 10 to the minus 2 moles of aluminum chloride. Okay. Now, what is this value in terms of? It's in terms of the entire reaction, right? So this is per 2 moles aluminum chloride, right? So if we're going to use this and convert it to enthalpy, or the heat generated, then we need 7.5 times 10 to the minus 2 moles of aluminum chloride. And this is minus 1390.81 kilojoules per 2 moles of aluminum chloride. Okay, so we got to divide 2 into this. So it's still in my calculator, so I'll divide 2, and then 1390.81. So that's a minus 52.1 kilojoules. Okay? Yeah, close enough. Oh, no, I rounded wrong. It is 2. 52.2 kilojoules for that product to be formed. This is the trick here. I mean, you guys can do that all day long in your sleep. But this is the trick right here, to recognize that that enthalpy is in terms of 2 moles of aluminum chloride. Or if we were given a value here for chlorine, it would be per 3 moles of chlorine or per 2 moles of aluminum. That's the way you interpret enthalpies for a balanced equation. How many grams of aluminum are required? Well, okay, I messed up. Maybe I didn't. How many grams of aluminum are required to absorb or evolve 1 kilojoule of energy? All right, so now we're working backwards. Instead of going from grams of aluminum chloride to heat, we're saying we want to make this much heat out of how much aluminum. So do we need to do that? Or you just want to do it? We'll do it. We need 1 kilojoule of energy. So if we've got 1 kilojoule, 0, 0, 1 kilojoule of energy, And that's per 2 moles of aluminum. Okay. So we have minus 1390.81 kilojoules per 2 moles of energy. So this gives us the moles of aluminum we need. Okay. And then it wants grams, yes. So we need grams, 2698, wasn't it? Yeah, 2698 aluminum. There we go. So that, resolve that equation, that calculation, and that should give us um, 2 times that and 26.98 times that, and divide by this value. So I get, it's in standard notation. I came out with 3.9, no, 3.88. Let's see. 3 significant figures. Times 10 to the minus 2 grams. Okay, and that's equivalent to 0.0388. So this is another example of chemistry problems that are solved by dimensional analysis. Let's see, do we have any others that we want to deal with? Might get in the lab early today. Let's do another Hess's law. About that. This will be a challenge. Okay, we have these equations available to us. And we want to end up with this equation and its enthalpy. Okay. We have to be very methodical about this one. Do we need all of those equations? Well, let's see. Calcium carbide. Right? That's the same stuff miners used to put in their helmets and add a little water to it. And the reaction would produce acetylene gas. And then they'd light it, and they'd have a light they could see underground. Of course, there's a problem with that. Open flame in a coal mine, right? Oops. Okay. So, this is the reaction. Yeah. Calcium carbide and water makes calcium hydroxide and acetylene gas. And then they burn the gas. Okay. So we want to find out how much energy is enthalpy associated with that reaction based upon these reactions. Well, there's calcium carbide. Let's see, where is it? Here it is, right here. Calcium carbide. So we need to flip this one around like that. And that makes this one positive. Okay? So we got calcium carbide on that side. How about water? There's water. Is there any other water? There's water here. Calcium hydroxide is correct on that side. So we got this one, and we got this one. Calcium hydroxide and the water. How about acetylene? There's acetylene. This one needs to go the other direction. You need to flip it. Right? Put acetylene on this side over here. And there's one of them here. Okay. So that one flipped will be good. But the sign here needs to change. It needs to be a positive. Okay. What about the others? Well, these might have to be used to cancel terms out of the other three. Right? Because calcium carbide here is okay, but there's calcium and carbon, graphite, right? Is there any calcium or carbon graphite in there? No. So now that this calcium and carbon graphite are on that side, we need calcium and carbon graphite on this side. There's the calcium. Okay, so that one's good. And the graphite here needs to be on this side because we flipped it. So will that get rid of, there's only one here. And there's two there. So this needs to be 2 times. So now this one is minus, so can I do this in my head? 2, 0, 1, 6, 7, 18, 67. So now we're going to use this one for that one. And this is 2 here, 2 here, 2 here. And that's good because this one flipped and put 2 carbon dioxide on that side. This will cancel those out. And this gives us 2 oxygens here with 5 halves on that side of oxygen. But we got another half here. Okay, I'm going to have to start writing some of these out. That first one is going to look like this. Calcium carbide, solid, yields calcium plus 2 graphite. Okay. And the second one is going to be as is. Calcium plus a half oxygen yields calcium oxide. Okay. And then the third one is as is, calcium oxide plus water yields calcium hydroxide. Okay. And we only changed the signs here. We didn't have to change the amount there because we multiply by a constant. That's 3, 4. We need to flip that one. 2 CO2 plus water yields acetylene plus 5 halves oxygen. Okay. And then the last one, as is with our change, 2 carbons with 2 carbon graphites, okay, plus 2 oxygens yields 2 carbon dioxide. Okay, now let's see, will that give us the target equation? Calcium carbide needs to be on the left-hand side, right? It's nowhere else but here. That was good. Calcium carbide. Okay. Waters. Let's see. There's a water. And there's a water. 2 waters. Right? So those are taken care of. How about on the other side? Calcium hydroxide. 1 calcium hydroxide here. Okay. And acetylene. Right there. See, I'm going to better put it down here. C2H2. Takes care of acetylene. Okay, is that everybody? 1, 2, 3, 4 terms. 1, 2, 3, 4 terms. That means that everything else has to cancel. Calcium. Calcium. That one cancels. That one cancels. Graphite. two of those, two of those. Carbon dioxide, two of those, cancel. Let's see, calcium oxide, 1, 1. Okay. Oxygen, 2 plus a half, 2.5. Is that 2.5? Yep. That one, and that one cancel. Let's see, we have any leftovers? Oh, that's good. So now we can add these values up. So we're going to use this one, this one, this one, this one, and this one. All right, let's see if I get the same numbers. Well, yeah, the one that's right there. Okay, 62.8, these are all in kilojoules, minus 635.5, minus 653.1. Yep. Plus 1,300. And minus 787.02. So I get, let's see, rounded off, minus 7.13 times 10 to the minus 2. Yep, that's it. Oh, excuse me, not minus 2, plus 2. Can you read my own calculator? Okay, I know it took a while, but that's the way it's done. Sometimes, this is a perfect example of, we only needed 3 of those equations to give us these down here. But in the process, we accumulated some extra things that aren't in the target equation, and they had to be gotten rid of. So that's what the other equations did for us. Okay. Well, let's see. So much for Hess. Let's see if there's anything else that needs to be dealt with here. Okay, you guys can do internal energy. That might be. So jump around, confuse everybody. I'm looking at number 8, right? I think that's a little more than we want to deal with. Oh, here's one we haven't done yet. Uh, 99. Chops off the bottom. Is that the answer? No, E's not the answer, so we'll let it slide. Okay. Nitric acid, HNO3, which should have an aqueous out here, was first prepared 1,200 years ago by heating naturally occurring sodium nitrate, also known as saltpeter, with sulfuric acid to produce sodium bisulfate. This is sodium bisulfate. Bi adds a hydrogen in there. Sodium sulfate would be Na2SO4, just like sodium carbonate, Na2CO3, and sodium bicarbonate. Baking soda is NaHCO3. So in this case, NaHSO4 is sodium bisulfate, and collect the vapors produced. Okay, and that's been going on for, well, it says 1,200 years or more, because this slide set is a few years old. Okay, calculate the delta H for the reaction here. Okay, this is a case where you can take the heats of formation and solve the problem. We have the heats of formation for each of these: sodium nitrate, sulfuric acid, the sodium bisulfate, and the nitric acid, which is in this gaseous form. Now, HNO3, is that in its standard state, is it a gas? No, I think it is. If it's not dissolved in water, I think HNO3 is a gas, like hydrogen chloride is a gas, until you put it in water and then it's hydrochloric acid. Right? So that's right. Standard states. Okay, so how do we deal with this? You take the standard heats of formation for each of these products and subtract the heats of formation for the reactants. Being careful, observing that you take into account the coefficients. First thing we need to do is say, is this balanced? Because if it's not balanced, we have to do that first. So we got one sodium here, one sodium there. Okay, good there. One nitrate here, one nitrate there. Two hydrogens here, one hydrogen there, and one hydrogen there. One sulfate there, and one sulfate there. That one's balanced. And they're all coefficients of 1. So all we have to do is say, this one here, this is product, and this one, product, minus this one, reactant, and this one, reactant. Okay, and we should get the correct answer. So products first, minus 1125.5, and they're all in the same units of measure. That's important also. Let's see, 11225.5, and the other product 135.1. Okay. Then we want to subtract this one, which makes the sign positive, 467.8. And the other one, 814.0, which is negative. So that one needs to be made positive also. And I get 21.2. Yeah, 21.2 right here. Kilojoules. Okay. When you've got the information, that's actually easier than Hess's law. A lot easier than Hess's law. Okay.